basics of MRI physics. Not an easy topic, often a daunting topic. It's something a lot of radiologists struggle with. It's difficult to master, so I tried to explain this as easy as possible, not just for you, but also for myself. And let me know at the end of this presentation if I succeeded or not. What am I going to talk about? I'm going to start with the basic principles of MRI physics. We're going to apply that to how we can use MRI to generate those MRI images, what determines the imaging characteristics and the image contrast we see in, for instance, T1 weighted images and T2 weighted images. I'm going to talk about some of the basic MRI sequences, what things look like on them and how we generate them. Some more specific MRI sequences like 3D sequences, for instance, and some advanced MRI techniques like fMRI, spectroscopy, MRI perfusion, and diffusion tensor imaging. Let's start with basic MRI physics. Now, what is the absolute basis on which everything is built? Two principles. First of all, atoms with an odd number of protons or neutrons have spin. And spin is basically a quantum mechanical, concept, but we can try to visualize it as an atom spinning around its own axis. That's not what really happens, but it helps us understand what's happening there. And the second thing we have to know is that a moving electric charge produces a magnetic field. That's the law of Faraday. And vice versa. A moving magnetic field or an oscillating magnetic field will induce an electric current in a conductor. And that's basically what MRI is based on. So on this image, on the previous image, we see a spinning atom. Normally there was, but it's not happening. This was supposed to spin, but it's not doing that, apparently. And this illustration shows us moving electrons, and these moving electrons generate a magnetic field around them. And here we see electrons being induced by a magnetic field around the magnetic field. And this is an illustration of the magnetic of an MRI bore, which is basically a gigantic magnet with a north pole and a south pole. So to summarize, we start with the fact that atoms with an odd number of protons or neutrons have a spin. Spinning atoms have a magnetic field because, well, basically they're a moving electrical charge, so they have a magnetic field or they induce a magnetic field, and we can consider those spinning atoms like tiny magnets. And luckily for us, our body is filled with these tiny little magnets. We can basically use any kind of atom with an odd number of protons or neutrons as the basis of our MRI signal, but we have chosen protons. Protons just consist of one proton, so we have an odd number of protons there. And our body is filled with them. We have about 4 multiplied by 10 to the 27th. I can't even visualize that number. I don't even know. I have to call it a billion or something like that. Probably more protons. So that's a lot. And these are tiny little magnets, but they are completely randomly aligned in the body. And that explains why our body in a normal situation has no magnetic characteristics. That's because all these tiny little magnets are randomly aligned and they kind of neutralize each other's magnetic effects. Now, what is the basics of MRI? Basically, we have 5 steps. The first one is we place the patient in a very strong external magnetic field, and that external magnetic field is generated by the MRI machine. Secondly, and I'm going to explain what these things mean later, we send a radiofrequency pulse, which is basically an oscillating magnetic field. We send that in the patient, and it is transmitted by a device called a transmitter coil. And this is basically sending energy under the form of an oscillating magnetic field in the patient. Then we turn that radiofrequency pulse off, and As a consequence, the patient will emit an electromagnetic signal, more specifically a magnetic signal, and that magnetic signal is once again captured by the coil I talked about. That coil can transmit things, it can also receive things. In this case, it receives the magnetic signal coming from the patient, and it translates that into, by the laws of electromagnetic induction, it translates that in an electrical signal, and that electrical signal is analyzed by a computer, and the end result is our image, or MRI image. So that's basically what involves or entails an MRI examination, these 5 steps. Let's go over these 5 steps one by one, the first one being the patient being placed in an external magnetic field. So here we see the MRI machine again, which is basically a very large magnet, and which creates a very strong external magnetic field with a strength of, in most clinical machines, 1.5 Tesla or 3 Tesla. And this is the magnetic field denoted by B0. And it points in a specific direction, so it's a magnet, so it has a north pole and a south pole. And what happens if we put a body in there, if we put a human being in there? Well, that human being is composed of 4 times 10 to the 27th number of protons, so a lot of tiny little magnets, completely randomly aligned. And the net magnetization of the body in a normal situation is 0. If we put that body in a very strong external magnetic field, these magnets will align along the axis of that strong magnetic field. And the result is that our body will become magnetized. Mind you, it's still a very tiny magnetization. The body is very weakly magnetized, but it suffices. We're going to use that magnetization to create the MRI image. And that magnetization is small because, well, we have a lot of protons in the body, but the protons can align themselves along the axis of the main magnetic field in 2 directions, either parallel to the axis, which is a low energy state, or anti-parallel, which is a high energy state. There are a limited number of protons, more, that align themselves parallel than anti-parallel, so the result is we get a very weak net magnetization vector given by mz in the human body. So we have generated some magnetization there, that's fine. What's happening next? Well, first thing is the protons will align themselves along the axis of the external magnetic field, but they will also do something else. They will start precessing. And what is that? That's not the same as spin. So spin is basically the axis spinning around the proton, spinning around its own axis. It's an intrinsic property of nuclei, giving the magnetic momentum of the nucleus. Precession, on the other hand, is something else. It's the circular movement of that magnetic momentum when placed in an external magnetic field. And we can compare it a bit with a spinning toll. So that tolls around its own, and is almost falling but isn't. So it's a bit similar. So precession is not the same as spin. So these protons perform that precession movement with a very specific frequency, and we call that the Larmor frequency. And I'm going to avoid mathematical or physical formula as much as possible, but this one is, I believe, basic for most radiologists. The Larmor frequency is given by the gyromagnetic ratio, given by the simple symbol gamma over here, multiplied by the external magnetic field. And for protons, the gyromagnetic ratio is 24.85 megahertz per Tesla. So that means that if we place a human body inside an external magnetic field or an MRI machine of 1.5 Tesla, the frequency, or the Larmor frequency, of the protons in the body will be 63.87. So this is for a 1.5 MRI. If you want to know what it's going to be in a 3 Tesla machine, just multiply 43 with 3, and that will be about like 129. If I'm not mistaken. If I'm mistaken, let me know in the comment section. So, final result, protons have aligned themselves along the axis of the main magnetic field, and they are also precessing along the main magnetic axis with a specific frequency called the Larmor frequency. Okay, on to the next step. Basically, we've magnetized the body now, but we can't really measure that magnetization. Why? It's very, very tiny, and it's located along a very strong external magnetic field. If we were going to use some kind of detector, there's no way we can distinguish that very tiny amount of magnetization coming from the human body amidst that huge or massive external magnetic field. But we can do it if we were to be able to flip that body magnetization in another plane so that it's no longer along the plane of the main magnetic field. So the direction of the main magnetic field is along the z-axis. If we were able to flip the magnetization in the body given by this orange arrow over here into the XY axis, we would be able to measure it. So that is what we want to do. We want to flip the body magnetization in another plane, in this case a plane completely perpendicular to the external magnetic field. How do we achieve that? Well, we're going to use a radio frequency pulse for that, sent in by a so-called transmitter coil. This probably requires a little explanation. So, what is an MRI machine composed of? This is extremely basic, but we have main magnetic coils, gradient coils, and radio frequency coils. And coils are basically able to generate magnetic fields. What do they do? The main magnetic coil is responsible for the generation of the main magnetic field, which in clinical MRI machines is generally 1.5 or 3 Tesla. Then we have the magnetic gradients, which are created or induced by the gradient coils. What is that? It's also a magnetic field, but it's not uniform. It doesn't have the same strength. The strength varies linearly with the location of the gradient, and it is superimposed on the main magnetic field. So what are we doing? We are basically adding some magnetization, and that can be along the axis of the main magnetic field, but it can also be in another plane. And we are going to change the magnetization, the main magnetization, a tiny little bit. And that change will vary depending on the exact location. So we have a very weak additional magnetization over here and a stronger additional magnetization over here. So we can perform that in any plane. So generally we have 3 sets of coils, one in the Z plane, so along the main magnetic field, and also in the X and Y planes, perpendicular to the main magnetic field. And these are important for the spatial encoding of the MRI signal. I'm not going to talk about that because I consider it already a bit more advanced, but just remember it. So this is important for the spatial encoding. So basically the body emits a magnetic signal, but if we detect that magnetic signal, we want to know where it is coming from. That's why we need spatial encoding, but I'm not going to talk about that as said. And we also use the gradients for the creation of specific MRI sequences, but more about that later. And then what I wanted to show you is the radio frequency coil. What is the radio frequency coil? It's a coil that transmits energy in the body under the form of an oscillating magnetic field. That's important, oscillating. So it's like moving while the main magnetic field and the gradients are basically static magnetic fields, so they don't change. So okay, we transmit energy, but we can also detect magnetic signal emitted by the body. So those radio frequency coils can do 2 things. They can transmit a magnetic field or an oscillating magnetic field, or they can detect an MRI signal, a magnetic signal. And they will then translate that into an electrical signal. In this part of the examination, also notice that I've drawn two coils. One is built into the MRI machine, another one is basically a coil that can be put over the head, and we have other types of coils that can be used for body imaging or musculoskeletal imaging. So we can use coils that are located in the machine, or we can use coils that are put over specific body parts, like a head coil in neuroradiology. And we have coils that are just transmitting, coils that are just receiving, and coils that can do both things. They can transmit a radio frequency pulse. So this oscillating magnetic field is also called a radio frequency pulse. They can emit it or they can detect it. So, okay, in this step, we use a radio frequency coil, we put it on, and it will emit an oscillating magnetic field, a so-called radio frequency pulse. And it will do that in a direction perpendicular to the main magnetic field. And what happens if we do that? So this is the body inside the main magnetic field. We see a coil, we see a head coil over here, and we're going to assume that it can both receive and detect radio frequency pulses in this presentation. And notice that at this moment, the protons are aligned along the main magnetic field. Now, what happens if we emit a radio frequency pulse perpendicular to the main magnetic field, as shown over here? This will change the direction of the proton alignment. How does it do that, or how does it work? Well, basically, we send in a lot of energy. So in a normal situation, as shown over here, the body magnetization given by mz will be located along the z-plane, along the axis of the external magnetic field. Then we send in a radio frequency pulse. So basically we send in a lot of energy, and that energy will push the body magnetization out of the longitudinal plane and into the transverse plane, into the XY plane. I told you that the radio frequency pulse is an oscillating magnetic field, which means that it also has a specific frequency. The angle under which the body magnetization is pushed out of the longitudinal plane is called the flip angle. And basically that can be any flip angle, but for spin echo sequences, generally it's a flip angle of 90 degrees. And if we use a radio frequency pulse that flips the body magnetization over 90 degrees, we call it a 90 degrees radio frequency pulse. So this radio frequency pulse is given with a specific frequency, namely the Larmor frequency. Oh, wait a minute, the Larmor frequency is the frequency with which the protons are precessing in the body. Is this a coincidence? No. Why do we use the Larmor frequency? Because we want to use a physical concept called resonance. And what is resonance? Well, it's something every parent knows. So you have a lovely boy or girl who likes to swing on a, how do you call that in English? A swing set? I don't know, but you see the picture, so you know what I mean. So to do this efficiently, we just need to give a push each time our darling boy or girl reaches us. If we were to push too soon, for instance, if we were to push here or here, that won't do anything. If we were to push here, but not here, well, nothing is going to happen. We are not transmitting energy from ourselves to our darling child, and we won't push him higher. Resonance means that I give energy to an object with a frequency that is exactly the same as the frequency with which that object, or in this case a person, is performing a specific movement. And if I do that, I will transmit energy and I will push my child higher and higher with each swing. This is resonance, and we use that to push the protons, which are precessing with the Larmor frequency, out of the longitudinal plane. By applying an oscillating magnetic field, a radio frequency pulse, with the exact same frequency which protons are resonating, we use resonance, and we have a very efficient way of giving energy to these precessing protons for pushing them into the transverse plane. So I hope this is clear because it's a very important concept. So just compare the radiofrequency pulse with a parent and the precessing protons in the body with a child on a swing, and you know why the radiofrequency pulse needs to be given with the Larmor frequency. So immediately after the 90 degrees radiofrequency pulse, something else happens. So we then see that protons are spinning in phase. What does that mean? What does that mean? It means that their magnetic moments are synchronized and they are processing. So they started with a precession movement along the z-axis. We flipped them in the xy axis in the transverse plane, and they keep doing that precession movement with the Larmor frequency, and initially they all precess in phase. They all precess at exactly the same rate and all nice together. And now we have a movement of magnetic structures in a plane perpendicular to the external magnetic field, and this is a magnetic signal that we can detect. It's a moving magnetic signal, so it will induce an electric current in the radiofrequency coil, which can also be used as a detector, as said. And that electrical signal is the basis of our MRI signal. So we're done, right? We managed to do it. We managed to flip the body magnetization in the transverse plane, and now we have created a moving magnetic field that can be detected and translated in electrical signal and images. We're done. Well, no, we're not. Oh, this is another illustration showing you the concepts of moving in phase and out of phase, in case that wasn't clear. So in phase means all moving in pace. Out of phase is what you will see at a marathon. It's not the intention of marathon runners to run together in phase. No, you want to be the first. But some people have better stamina or better trained, just have better physique, and you will always have people who run faster, who will run slower, so you don't see people running in phase at a marathon, for instance. So, okay, to summarize, we give a 90 degrees radiofrequency pulse. This is adding energy or giving energy to the protons in the body, pushing them out of the longitudinal plane, and this is what happens. So the longitudinal magnetization of the body flips in the xy plane, and protons are now precessing in phase with the Larmor frequency. And then we turn off the radiofrequency pulse. What happens then? Now those protons can relax again. So we were giving them energy and energy to push them out of the longitudinal plane, out of the z-axis. Now we remove the energy, and it's like if we stop pushing our child on the swing, eventually, if he doesn't try to keep going higher himself, and our protons don't do that, they're lazy, they will start to relax again, and they will return to their initial situation. And what is that? Well, two things will happen. The body magnetization will return into the z-plane, and this is determined by a phenomenon called T1 relaxation. And what's happening also, the protons will lose their phase coherence. So initially they were precessing in phase, they will lose that precession in phase. So these are two independent, well, not completely, but let's consider them completely independent for the sake of this presentation to keep it easy. These are two independent mechanisms that happen simultaneously, which complicates it a bit to understand it, but we're going to address them one by one. They happen simultaneously, and T2 relaxation, so the dephasing of the protons, is something that happens faster than the T1 relaxation. So let's talk about T1 and T2 relaxation separately. So T1 relaxation, once again, let's summarize. I'm going to repeat myself a lot, but I think that's important to really understand it. When the radiofrequency pulse is turned off, protons will return to the axis of the main magnetic field. So let's look at what happens basically. So initially, all our magnetization after the 90 degrees radio frequency pulse is flipped in the transverse plane. If we now turn off the radio frequency pulse, we will see, so the magnetization along the z-axis in this picture, where is my mouse? Yes, in this picture is 0. If we put out the radio frequency pulse, gradually the magnetization will return. Not at once, but if we just wait long enough, we will see it gradually increase until it reaches its normal value again, the value it had before the radio frequency pulse. And if we look at these diagrams, or how should I call them, and if we try to connect them, so this is what happens over time, we see that the longitudinal magnetization gradually increases and it follows an exponential curve. We call that the T1 recovery curve until it reaches its normal equilibrium value. This is the T1 relaxation curve. And the T1 relaxation time, which is an important concept in MRI physics, is defined as the time it takes for longitudinal magnetization to reach 63% of its original magnetization. For those of you who like mathematics, here is the formula. The only thing that's important is that you know that it's an exponential curve as given by the formula. And what causes T1 relaxation? Well, basically protons want to be in a lower energy state. They were pushed into a higher energy state. They hate it. They don't want it. So what do? As soon as the radio frequency pulse is turned off, they release all the energy they received from the radio frequency pulse into the surrounding environment, which is also called the lattice, under the form of heat. And that is why we slightly become warmer discreetly, but it happens during an MRI examination. And this also explains why synonyms for T1 relaxation are longitudinal relaxation, because we get relaxation towards the longitudinal plane, thermal relaxation because we release heat, or spin lattice relaxation because we give energy to the surrounding environment or the lattice. And also important, the T1 relaxation time will differ between tissues, and that is something we can use to create MRI images, because it will depend on the interactions between protons and the surrounding environment, and that surrounding physical or chemical environment will be different in different tissues. So let's now move on to T2 relaxation. So immediately after 90 degrees radio frequency pulse, protons were precessing in phase in the transverse plane with a Larmor frequency, but that doesn't last very long. Nevertheless, so this is, if we were to look at the XY plane from above, we see the protons moving in phase, but only for a very short amount of time. Now, these are moving protons, so they are charged particles, so this induces a magnetic field, and each time those moving protons pass here, for instance, where a detector is located or a coil is located, this will create a signal that can be picked up. So it is basically this sweep of magnetization in the transverse plane that induces a current in the receiver coil. But, this is another slide. Protons, however, start precessing out of phase very quickly. So if we now look at another way to visualize it, so this is nice, I'm going to show it again, just because it took me an awful lot of time to create this PowerPoint slide. So let's admire it a bit. So we see these protons moving out of phase, it's beautiful. Okay, and let's now look at this other depiction of T2 relaxation time, just to make it really, really clear. So this is basically the net vector magnetization, and all protons are spinning in phase immediately after the 90-degree radio frequency pulse, but then we put it off and they start spinning out of phase. Some of them start precessing a little bit faster, some a little bit slower, and if we just wait long enough, and basically it doesn't really have to be that long because T2 relaxation happens pretty quickly, No phase coherence is left. And it also means that the magnetic signal in the transverse plane will have become very, very weak. And for some reason, I found it necessary to illustrate the same concept with yet another image. But this time, take a careful look at this here. This is the magnetization in the XY plane. This is wrong. And we see that, of course, as protons start dephasing, this will become weaker and weaker and weaker. And this is basically similar to T1 relaxation, in which the longitudinal relaxation increases. In T2 relaxation, the transverse magnetization becomes weaker and decreases. So, and because this is the basis of the measurable signal, that will also become very weak. So this is the depiction of the magnetic signal. Once again, this is wrong. This should be XY. So here we have once again, seen from above, protons precessing in phase initially, but normally this vector or this arrow, which basically denotes the strength of the magnetic field in the XY plane, it should become smaller with every spin due to dephasing. So basically it should form this shape, so not a circle but a spiral, gradually becoming weaker and weaker and weaker. And this here shows us the magnetic signal that is detected by a receiver coil, and with each sweep, so here it reaches, let's say, this point where it is located, then it goes back to the other side, so the signal becomes weaker, inverts, then it comes back again, but we see that it has become smaller. The peak is smaller due to phase loss of phase coherence, and this happens with every sweep. And then we get a curve looking like this, and this also follows, this is also an exponential curve, but a decreasing exponential curve. This is the T2 relaxation curve. So let's look at this curve over here. How do we define T2 relaxation? It is the time it takes for transverse magnetization to be reduced to 37% of its initial maximal value. So it's a decreasing exponential curve. T2 relaxation is also known as spin relaxation or transverse relaxation. Transverse relaxation because it is relaxation happening in the transverse plane. Spin refers to one of the possible mechanisms responsible for this decrease in transverse magnetization. Now, T2 relaxation and T1 relaxation happen simultaneously. And any process resulting in T1 relaxation will also result in T2 relaxation. So as T1 relaxation increases, T2 relaxation will also increase. There is also T2 relaxation independent of T1 relaxation, and that has two components or two reasons. One is intrinsic, the so-called spin-spin aspect, and one is due to extrinsic factors. So let's explain those a little bit further, and I hope you are still with me. What is causing protons originally precessing in phase to lose that phase coherence? We have true T2 decay, which is due to intrinsic factors, and we have extrinsic factors. Now, the intrinsic factors is the result of interactions between spins, so-called spin-spin interactions, and we also call that true T2 relaxation, which is irreversible. It occurs because these spins have tiny magnetic fields, and they will influence the tiny magnetic fields of other neighboring spins. And basically, simply by being in each other's vicinity, spins will cause each other to lose phase coherence in the transverse plane. So this is true T2 decay, spin-spin interactions. And then we have extrinsic factors, which have nothing to do with the fact that spins are located next to each other and will influence each other. No, this is caused by factors located at the level of the magnet, at the level of the MRI machine, or at the level of the body. And what exactly are those? Well, first of all, we always assume that the external magnetic field generated by the MRI is like this perfect uniform magnetic field, but that's simply not true. A perfect magnetic field exists somewhere in the universe, or in physicist's mind, but in reality, a main magnetic field is not perfect. There are very small variations in the main magnetic field, and these very tiny imperfections, also called inhomogeneities, will, of course, cause protons to have slight variations in their Larmor frequency, and this will induce dephasing of the spins. There are also variations in the magnetic properties of tissues or materials, which create local disturbances in the magnetic field. For instance, if you have a hemorrhage in the brain, even if it's small, you will find a lot of iron there, because blood, hemoglobin, contains iron, and iron is paramagnetic. It's very magnetic. So that will change the magnetic properties of the tissue and have an influence on the magnetic field. It will cause protons to dephase more rapidly. So the combination of these factors, so imperfections in the magnetic machine and small variations in the magnetic properties of tissues, will also contribute to T2 relaxation. So let's now also introduce the concept of T2 star relaxation. What is T2 star relaxation? It's basically a combination of what I just called the true T2 decay caused by spin-spin interactions, combined or with the T2 prime effects. So basically the T2 relaxation due to extrinsic factors like imperfections in the main magnetic field or susceptibility differences between the body tissues. And this I already explained. This is true T2 relaxation, and because T2 star relaxation is a combination of true T2 decay and these extrinsic factors, T2 star relaxation will always be faster than true T2 relaxation. And T2 star relaxation is basically what we see after we have given that first 90 degrees radiofrequency pulse. It's a combination. We see loss of phase coherence due to true T2 decay and due to extrinsic factors, the T2 prime effects. Now, T1 and T2 relaxation, as said, happen simultaneously, but T1 relaxation will generally always be faster than T2 relaxation. Theoretically, they can be the same. In practice, T2 relaxation will always be faster, and T2 relaxation will never be faster than T1 relaxation. So T2 relaxation happens faster than T1 relaxation. Okay, I think this is clear, or I hope this is clear, so we can move on to the next step. What happens now? The patient will emit an electromagnetic signal. We have flipped the magnetization of the body and the transverse plane, so now it can be detected. We've already seen this figure. This is looking from above on the XY plane, and we see protons spinning in phase for a very short amount of time in the XY plane. And as already said, the sweep of magnetization can be detected by a receiver coil and will induce an electric current in that coil. But as also said, due to phase coherence, the signal in the XY plane becomes weaker with each sweep. So we have a receiver coil here. It picks up the signal best when the signal is over here, and if the signal moves away again, it will become weaker, and it will also become weaker with each sweep. So in the end, we get this as a signal, and this signal is called the free induction decay signal. Free because we have removed the 90-degree radiofrequency pulse, so the protons are free again to lose their phase coherence. Induction because it's a moving magnetic field and it will induce an electrical current in the receiver coil, and decay because it becomes weaker with each sweep. And it's basically it becomes so weak that we can't really use it to generate or create the MRI image. No, we want a stronger signal for that. How do we do that? So I think everything on this slide I've already told you. Here we see a receiver coil. which is located perpendicular to the moving magnetic field. Notice that it is a spiral as well. The result will be the free induction decay curve, and this is due to T2 star relaxation. So what do we do to create another signal also in the transverse plane that's more suitable, that's stronger, that lasts a bit longer, and that can be used to create MRI images? So this we have seen. This is phase coherence, which occurs after we turned off the 90 degrees radio frequency pulse. How do we get a new signal that's stronger? We apply another radio frequency pulse, but this time not a 90-degree radio frequency pulse, no, we apply a 180 degrees radio frequency pulse. So what do? We basically push the transverse magnetization into the transverse magnetization, but towards the other side. We make it flip 180 degrees. Why do we do that? Well, as said, the signal, the free induction decay signal, is too weak. We want a new signal, a better signal. We can compare this with our marathon runners. I already told you about the marathon runners. They are running out of phase. This guy is running really fast. This guy is running a lot slower. This guy will, the more time passes, be farther ahead of this guy. So the phase, this coherence will only increase with time. But now imagine that somebody were to say, stop, turn around. Everybody still keeps running at the same speed. This guy is still running quite slowly. This guy is running very fast. Now, if they were to turn around, they will eventually meet each other again, because this guy is slowly going back and this guy very quickly, so he will catch up with that guy. And that's what the spins do after we applied a 180 degrees radio frequency pulse. They catch up with each other. They were dephasing, they were losing their phase coherence, but after the application of a 180 degrees radio frequency pulse, they will regain their phases again. They will become coherent again. So this is just a lot of text, but I think I've said everything that's on here. So we flip the spins in the transverse plane by 180 degrees, and spins that were precessing faster are now behind, spins that were lagging are now ahead, but they are able to catch up with one another, and eventually we will get rephasing and a new strong signal. So this is the same concept but illustrated in a different way. So here on top we see what happens after we turn off the 90 degrees radio frequency pulse. So the magnetization and the XY plane becomes weaker, but then we turn on the 180 degrees radio frequency pulse, and what do we see? We start with a weak signal, but the protons start catching up with each other and they gradually come together again, and as a result the magnetization and the transverse plane will increase until we get a moment of perfect phase coherence again. And that signal that we create this way is called the spin echo. And this spin echo is the basis of our MRI image. So the same concept, once again illustrated in a different way, because I think these kind of visuals really help you understand this quite difficult topic. This is the 90 degrees radio frequency pulse, which abuses the free induction decay signal. Too weak, we can't use it. So we apply a 180 degrees radio frequency pulse and we generate the spin echo, which lasts longer and can be detected by the radio frequency coil and is the basis of the MRI signal. I'm going to introduce a new concept here, which will return later on, the echo time. And the echo time is the time between the start of the application of the 90 degrees radio frequency pulse and the time the spin echo was created. The 180 degrees radio frequency pulse is given at the echo time divided by 2. So this here is echo time divided by 2, and this half is also echo time divided by 2. So the spin echo signal is used for the creation of the MRI image. this is a conventional spin echo sequence, and well, one spin echo is not enough. We're going to repeat it a number of times to create a lot of spin echoes. Here we get this helps us introduce a new concept, the repetition time, which is the time between the start of successive pulse sequences. We call this a pulse sequence, the 90 degrees, 180 degrees radio frequency pulse. There are a lot of variations on it, but it's called a pulse sequence, and the repetition time is the time between the pulse sequences. And this is the spin echo signal, and as already said, the echo time is the time between the 90 degrees radio frequency pulse and the center of the spin echo. Okay, this brings us to the last step, the detection of the signal by a receiver coil and using it for the generation of an image. I am not going to talk about that. Why exactly? Because, well, for image generation, I already touched upon that. We need to be able to detect what part of the body the signal is coming from, spatial location. I could do a presentation on spatial location of the MRI signal, but it will definitely take me a lot of time, and it makes the topic even more complicated than it already is. I'm going to focus on the basics now. And what are the basics? Let's repeat. We start with spinning protons in the body, spinning randomly in all directions. The net magnetization of the body is 0. We place these spinning protons in a strong external magnetic field, and they will align themselves along the axis of the main magnetic field, and they will also start precessing along the external magnetic field with a frequency given by the Larmor frequency. Then we want to flip that body magnetization in the transverse plane, and we do that by applying a radio frequency pulse. Basically, we give a lot of energy to these spinning protons, and this pushes them in the XY plane. Now, normally they shouldn't, this is the wrong animation, they should stay there, so they're not coming back. And then we turn off the radio frequency pulse, and because of T1 relaxation and T2 relaxation, the protons will become, or the magnetic field in the XY plane will become weaker. T1 relaxation will make the protons return to the longitudinal plane, and T2 relaxation will make them lose their phase coherence in the transverse plane. Now, by applying a 180 degrees radio frequency pulse, we create another signal, the spin echo signal. And this signal is finally used for the creation of our MRI images. So this is the absolute basis of how we create MRI images. So I'm not going to talk about spatial location. I want to talk about tissue contrast, because when I said we use this to create an MRI image, well, there are a lot of different types of MRI images. We have T1 weighted sequences and T2 weighted sequences, which are the workhorses of MRI images, and basically most of our sequences are derived from that, to put it easily or to put it simply. But what makes these sequences different? Why do these images look different? The basic principles are the same. What makes them different? Let's talk about that now. So here we have T1 weighted images and T2 weighted images. What determines the difference, or how do we get these different images using the same physical principles? Now, first we need to define what tissue contrast is exactly. What do we mean with tissue contrast? If we want to examine a certain body part, or if you want to detect pathology, it's important that you can distinguish the various components of that organ. For instance, the brain contains white matter, gray matter, there is water in the ventricles, it is surrounded by bone, by a scalp. We want to be able to distinguish all these parts, so we need to see a difference in the signal intensity of these different tissues to be able to recognize them on an image. That is what tissue contrast is. So tissues have, that's what determines the tissue contrast in an MRI, basically three things. Tissues have differences in their number of protons, and their T1 relaxation times and their T2 relaxation times. And we can use these differences between tissues to generate different types of images, each showing different contrasts between the various parts of an organ. This is an example of T1 and T2 relaxation times for various tissues in the brain or in the central nervous system. So the number of protons is quite similar, not 100%, but let's just assume it's quite similar. We're going to focus on differences in T1 and T2 relaxation times. Look at the T1 relaxation time of water and fat, for instance. There's a huge difference there. So if we were to create an MRI image emphasizing the difference in the T1 relaxation time, we should be able to see a lot of difference between water and fat. How do we do that? We're going to, my apologies, we're going to work further upon this example. Here we have the T1 relaxation time of water and fat. So if we were to look at the T1 relaxation curve for water, that would look a bit like that. So water has a long T1 relaxation time, so it reaches 31%, 63% rather, of its equilibrium after a pretty long time. And fat has a very short T1 relaxation time, so the curve for fat would look a bit like this. So we see that there's a huge difference at this time point here. Here, if we wait a very long time, so T1 relaxation happens after we flipped our protons in the transverse plane. We turn off the radiofrequency pulse, they return. So if we wait a long time, the magnetization will have completely returned in the Z-plane. So if we were then to do another pulse, well, we would basically flip the same amount of magnetization in the transverse plane, and there would be very little differences between water and fat. This is the point we have to use, where there's a huge difference in the T1 relaxation of water and fat for the creation of our MRI image. So how do we do that? I already explained it a little bit, but let's illustrate it with figures to make it more clear. So this is a 90-degree radiofrequency pulse. It flips the body magnetization in the transverse plane. And of course, the magnetization is a bit different. Or tissues have different magnetic properties. If we wait a short amount of time, let's say 200 milliseconds, we will see that a lot of fat magnetization will have already returned completely in the longitudinal plane. It will have almost completely recovered. However, for water, in the same time period, only a little bit of magnetization has recovered. So if we were to perform another pulse sequence now, we would actually flip a lot of fat magnetization in the transverse plane, but not a lot of water magnetization, because this is the signal used for the creation of the MRI image. Fat will have a high signal because there's a lot of fat magnetization in the transverse plane. Water, however, will have a low signal because there is very little water magnetization in the transverse plane. The result is we will see a high contrast between fat and water. So how do we do that? How do we exploit the T1 relaxation differences between water and fat for the creation of high contrast between these two structures? We have to perform a new sequence after a short amount of time. Why? If we wait a long time, both water and fat will have completely recovered the longitudinal magnetization. We need to do it when fat has recovered a lot and water a little, so where the difference is the biggest. So we basically need a short repetition time. If we choose a long repetition time, these structures will look exactly the same. By choosing a short repetition time, these structures will look very differently, and fat will have a high signal, water a low signal. This is a figure I did not make myself. It's one I took from the internet, but I found it very interesting. This is basically what happens if we give or start a new pulse sequence after a certain amount of time. So this is the recovery of the longitudinal magnetization for fat, gray matter, and water. So if we were to start a new pulse sequence after 1000 seconds, we will see that most fat has recovered its longitudinal magnetization, and if then flipped in the transverse plane, we will have a high signal. It will be lower for gray matter and will be very low for water. So let's maybe look at the video. Oh, I can't. Okay, let's look at that video again. So this is the recovery of the longitudinal magnetization. Then we start a new pulse sequence, and we get a lot of transverse magnetization for fat, very little for water, because water hadn't recovered yet in the longitudinal plane. And this slide is basically for my students for study purposes, because they can't remember everything I'm telling them. So every now and then I spell it out on a slide, but there's nothing new here. Okay, let's now talk about using differences in T2 relaxation. I'm going to illustrate differences in T2 relaxation between water and white matter. Water has a very high T2 relaxation time of 2000 milliseconds. So it takes a lot of time for the protons and water molecules, free water molecules, to lose their phase coherence. And for white matter, that happens very rapidly after 80 milliseconds. So if we were to draw the T2 relaxation curve for these two structures, that's what it would look like for water. And this is what it would look like for white matter. We see that there's a lot of contrast between the two, or a big difference in T2 relaxation times at this time point. How can we use this information to create an image with a lot of contrast between water and white matter? We do that by choosing a long echo time. And why is that? Imagine if we were to choose a short echo time, then basically both structures will have the same degree of magnetization in the main magnetic and the transverse plane, with very little difference between them. If we wait a longer time for the generation of the echo time, we will see a lot of difference. Why this echo time, or what's the relationship between the T2 relaxation and the echo time? Well, remember that the signal is basically the signal that is used for the generation of the MR image is the spin echo. And the spin echo occurs after the echo time, which is the time between the application of the first 90 degrees radiofrequency pulse and the actual spin echo. So T2 weighted images, or images in which the tissue contrast is mainly determined by differences in the T2 relaxation values of tissues. And we need, if we want to create images that show the difference in T2 relaxation values of tissues, we need to perform our sequence with a long echo time, because then the degree of dephasing of water and white matter, or the difference between the degree of dephasing, will be greater than if we do a short echo time. So let's summarize. We have talked about T1 and T2 relaxation, and repetition time and echo time. Repetition time is the amount of time between successive pulse sequences. And if we choose a short repetition time, this will emphasize T1 differences between tissues. The echo time is a time from the center of a radiofrequency pulse to the center of the echo, or from the beginning, I believe, of the radiofrequency. I'm not sure. Maybe center. Anyways, if we choose a long echo time, this will emphasize T2 differences, and we basically can control that by choosing when we're going to apply the 180 degrees radiofrequency pulse, because that's basically the echo time divided by 2. This should be TE divided by 2, not T2 divided by 2. So I hope this is clear. If we perform sequences and we use a short repetition time, we will accentuate the T1 relaxation differences between tissues. So T1 weighted images, or images made with a short repetition time, and what we see then is basically a visualization of the different T1 relaxation times of tissues. And a T2 weighted image, we choose a long echo time, and then we get images in which the image contrast is mainly determined by differences in the T2 relaxation times. Of course, you also have T1 and T2 effects in both kinds. You never have a pure T1 image. The image contrast is determined by both T1 and T2 effects. But if we want a T1 weighted image, we're going to minimize the impact of differences in T2 relaxation times. And how do we do that? By choosing a short echo time. So in T1 weighted images, we have a short repetition time and a short echo time. In T2 weighted images, we use the long echo time to make use of the difference and T2 relaxation values between structures, but we also use a long repetition time to minimize the impact of differences in T1 relaxation times between tissues. So this is the same illustrated in yet another way. T1 weighted images have a short echo time, a short repetition time, and a short echo time. T2 weighted images are made by using a long echo time and also a long repetition time. Then there's a thing called proton density images. What are those? Well, if we use a long repetition time, the longitudinal magnetization due to T1 relaxation will have almost completely recovered. So the tissue contrast will not be determined by differences in T1 relaxation values. If we use a short echo time, almost all magnetization of tissues, any tissue, will still be in the transverse plane and still be strong in the transverse plane. So the difference in contrast between tissues will not be determined by the T2 relaxation values. What then determines the image contrast in this image? Well, basically the number of protons, and that's why we call them proton density images. And finally, what if we were to do images with a short repetition time and there's barely any longitudinal magnetization, and a long echo time when basically all magnetization in the transverse plane has disappeared or has become very small, then we get very crappy images with very poor image contrast. So, and another slide to illustrate once again what I just said. I'm not going to read it out loud. This is more for my students, so they can use that for their study purposes. Okay, now we are ready for the next part, recognizing MRI sequences. I will upload this part in a separate video because this presentation is otherwise becoming very, very long.